When people say that Isaac Newton completely transformed the field of physics, they really aren't kidding. Now we've already talked about his three laws of motion which we use to describe how things move. But another of Newton's famous contributions to physics was his understanding of gravity. Odds are you've been told the story of Newton's apple at some point. The story goes one day he was sitting in his mother's garden when an apple fell out of the tree. That's when Newton had his grand realization. Something has been pulling the apple down to earth. And that led to another idea. What if the apple was pulling on earth too, but you just couldn't tell because the effect of apple is less obvious? A few years later, Newton was sitting in the same garden when he had another stroke of inspiration. What if the same force that pulled the apple to the ground could affect things much more farther from Earth's surface, like the moon? It was kind of counterintuition because the moon orbits Earth instead of crashing straight into the ground like an apple that falls off a tree. But Newton realized that the moon was still being pulled towards Earth. It was just moving sideways so quickly that it kept missing. That's what was keeping it in orbit.
Newton knew that, however this gravitational force worked, it would probably behave like any other net force on an object. It will be equal to that object's mass times its acceleration. The mass part was easy enough. It will just be the mass of the apple or the moon. It was going to be a little harder to figure out the factors that were affecting the acceleration part of the equation. The first thing Newton realized, when an object is close to the Earth's surface, like an apple in a tree, gravity makes the accelerate at about 9.81 meter per square. But the moon has an acceleration that's only about 3600 of that falling apple. The moon also happens to be about 60 times as far from the center of the Earth as the apple will be. A 60 square is 3600. So Newton figured that the gravitational force between two objects must get smaller than further apart they are. More specifically, it must depend on the distance between the two objects squared.
Then there was mass, not the mass of the apple or the moon, the mass of the object involved in gravitational force. In this case, Earth. Newton realized that the greater the masses of two objects pulling on each other, the stronger the gravitational force would be between them. Once he taken into account the distance between two objects and their masses, Newton had the most of his equation for the way gravity behaved. The gravitational force was proportional to the mass of the two objects multiplied together, divided by the square of the distance between them. But it had to be a lot smaller, or else you would see a force pulling most everyday objects. So Newton added a constant to his equation, a very small number that would make the gravitational force just a tiny fraction of what you calculate otherwise. He called it G, and he called this full equation F equals to Gmm over r squared, the law of universal gravitation. Newton had no idea what number big G would be, though. He just knew it would be a tiny number and put the letter G into his equation as a placeholder.
About a century later, Henry Cavendish, another British scientist, made careful measurements with some of the most sensitive instruments of the time and figured out that G was equal to about 6.67 times 10 to the power of negative 11. So indeed, Newton was right about big G having to be quite small. But even though he didn't know the exact value of big G at the time, Newton had enough to establish his law of universal gravitation. He described gravity as a force between any two objects and published his equation of calculating that force. There's one more thing we should point about Newton's law of universal gravitation, which is that it fits what we expect the equation for a net force should look like according to Newton. From Newton's second law of motion, we know that a net force is equal to the mass times acceleration. What the law of universal gravitation is saying is that when the net force acting on the object comes from gravity, the acceleration is equal to the mass of the bigger object, like Earth, divided by the distance between the two objects times big Earth. The gravitational acceleration at Earth's surface is small g. Small g is actually equal to big G times Earth's mass divided by Earth's radius squared. So, hundreds of the years after Newton's day, NASA is still using his maths. Today, we learn about how Newton came up with his law of universal gravitational acceleration.